Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you. Today we will solve problem 5.6. The statement of problem is given that for the beam and bending shown, first draw the shear force and bending moment diagram. The second part is determine the equation of shear force and bending moment curve. So let's start. You can see that the beam of length L is given and the load from point A to B is uniformly distributed load. Similarly, from point B to C there is no load, and from C to D again there is a distributed load. So first we will find the reaction forces at point A and D. So for that we will draw a rough figure of the beam. For example, this is the beam. So there will be a reaction force that is represented as RA, and reaction force at point B is at point D is RD. Now for uniformly distributed load, if you want to convert it into concentrated load, so you will have to multiply with this W with this A. So that will be W into A. Similarly, here again W into A. But now this WA will be at a distance of A by 2. And similarly, this will be also at a distance of A by 2. The total length of the beam is L. So first we will apply the equilibrium equation, that sum of all forces along y direction that must be equal to 0 and upward force is positive. So now we can see that there are four forces: RA plus RD minus W into A and again minus W into A. Their sum must be equal to 0. So from that we get RA plus, this is RD. RA plus RD is equal to 2 times WA. So this is the first equation that we get from the sum of all force along y direction is equal to 0. Now there are two unknowns and this is one equation, so we cannot find the forces from this. So we have to take the moment equation as well. Sum of all moment you can take either at A or point B. So D. So let's take the moment about point D is equal to 0 and counterclockwise is as positive. So now you can see that RA is the force which is producing a rotation in clockwise. So that will be minus RA into L. Again, this force WA is also producing a counterclockwise rotation, so it will be positive. Now WA is the force and you have to multiply this distance. Now this distance is L minus A by 2. Similarly, this force WA is also producing a counterclockwise rotation. So this will be also WA. Now this distance is A by 2. That must be equal to 0. So we will get minus RAL plus WAL minus WA square over 2 and plus WA square over 2 is equal to 0. This will cancel out. So we will get minus RA into L is equal to minus WA into L. L will also cancel and minus minus sign will also cancel. So we will get RA is equal to W into A. So now we know this is, this is equation 2. So we will put this 2 in 1. So put 2 in 1. We will get R, this is again, this is RD. So RD will be equal to 2 times WA minus RA, and RA is WA. So 2 times WA minus WA, so RD will be equal to WA. So both the forces are same. Now we have find the reaction forces, which is like if I draw the reaction forces at this point, so this is RA, if I remove these supports, and this is RD. Clear? Now we will move toward finding the shear force equation and bending moment equation. So first we will take the section at this distance, between A and B. So from A to B, or we can say x is greater than 0 and less than A. So if I draw the beam like this, so this is reaction force at point A or A point. Clear? This distance is taken at a distance of x, and the distributive force is shown as W. Clear? So if you cut it over here, so definitely there will be a shear force V as well as bending moment M. So let this point is any point, let's say this point is J. So we will apply the shear force equation as well as bending moment diagram. So for shear force, we take the equation sum of all force along y direction is equal to 0, and taking upward force is positive. Now you can see there are forces acting on this section of the beam. The first one is RA, and RA is equal to WA. So WA minus this omega force, W force. And how we will convert this distributed load into concentrated? So you have to just multiply this W with is X. So that will be W into X minus this shear force V is equal to 0. It means that V will become equal to W if we take common A minus X. So this is the shear force equation. This is equation number 4. Now sum of all moment about point J is equal to 0, and this equation will be used for finding the bending moment equation from x is greater than 0 and less than A. So now you can see this force RA will produce a clockwise rotation. So that will be equal to RA is WA, so minus WA into perpendicular distance is X. Clear? This distributed load is also producing a counterclockwise, so it will be positive, and the value will be equal to W into X. This will be the magnitude, and it will be in the middle. So perpendicular distance will be X by 2. So into X by 2 plus this moment, that is counterclockwise. So that will be equal to 0. And if we solve this equation, the value comes out to be moment will be equal to W into AX minus X square over 2. Let this is equation number 5. Now this equation 4 and 5 is valid from point A till point B. Again, we will take the section at this point from B to C, anywhere from B to C. So for that, from B to C, from B to C means X is greater than A and less than L minus A. So X is greater than A and X is less than this distance from this point to this point. This distance is L minus A, because total is L, and if you subtract this A from this L, so this will be L minus A. So let's start. If we section it over here, and if I draw the beam, so let's say this is the section point, this is RA. Again, there will be a distributive force, and this distributive force is at a distance of A. And let from this point till this point, this is X. So again, if you section it over here, there will be a shear force V and a bending moment, reaction bending moment M. Clear? So we will find the shear force equation. Sum of all force along y direction must be equal to 0, and upward force is taken as positive. So you can see RA, that is acting upward. So RA is equal to WA. Now this distributed load, which will be converted into concentrated load when you multiply W with A. So that will be minus WA. And again minus this shear force, their sum will be equal to 0. It means that shear force is equal to 0, and this will be valid when X is greater than A and less than L minus A. Now we will find the bending moment. This taken as positive must be equal to 0. Again, let this point is J. So moment, we will take the moment about point J is equal to 0. Okay. So I think the lower portion was not visible. Now it's clear. You can see that this force RA is producing a clockwise rotation. So minus WA into total distance X. And this concentrated load, distributed load, that will be equal to, this also produce a counterclockwise, so that's why plus, so W into A. Now perpendicular distance will be, this distance is A by 2. Clear? So this distance is A by 2 and this is X. So this remaining, this distance from this point to this point is, this distance is X minus A by 2. So we will write X minus A by 2 plus this external moment, that must be equal to 0. When you solve this equation, so moment comes out to be half of omega A square. So this is the bending moment equation. Let this is equation 6, this is equation 7. So equation 7 is the bending moment equation, and it's valid for X is greater than 0 and X is greater than 0 and X is less than L minus A. Now we will move toward the third section, which will be C, between C and D. So from C to D, it means X is greater than L minus A and less than L. So we will take this section at this point. So here we will use the second, we will not take this portion. You can also take, but we will analyze this remaining portion. So if I draw this like, so this is the reaction force, which is RD, and this is the uniformly distributed load over here, that is omega. This distance was L minus X. Again, if you cut over here, so there will be a shear force which will be acting upward, because in this portion it will be downward. So in order to take it equilibrium, it will be upward, and there will be a moment M. Let this point is also, let's say this is J. So we will apply sum of all force along y direction must be equal to 0 and upward is positive. So you can see there are forces RA which is equal to RD, which is equal to WA. So WA, there is a force downward which is equal to minus W into L minus X, which will be acting downward, and there is a shear force that is equal to V is equal to 0. So from here we will get V is equal to W into L minus X minus A. So this is, let's say, equation number 8. And this is a shear force equation for the region when X is greater than L minus A and less than L. For bending moment equation, we will find moment about J is equal to 0 and clockwise is taken as negative. So you can see there is a clockwise which is equal to minus M. Clear? Moment due to this shear force, there will be a movement, this shear force will produce no movement because it is passing through J. Now this W force will create a clockwise movement, and this will be minus W into L minus X into, if this is acting at the middle, so this distance will be equal to L minus X over 2. So into L minus X over 2 plus this RD force which is producing a counterclockwise rotation. So RD is equal to WA and perpendicular distance is L minus X. Their sum is equal to 0. So we will get moment is equal to W into A into L minus X plus half of L minus X whole square. So this is equation number 9. Now equation number 9 is the bending moment equation for the region X is greater than L minus A and X is equal to X is less than L. Now we will draw all these equation 4, this equation 4 and this equation 5 is the bending shear force equation and bending moment equation for region X is greater than 0 and less than A. Again, for region of X is greater than A and less than L minus A, the shear force equation is this one and bending moment equation is this one. For region X is greater than L minus A and less than L, so we have shear force equation this and bending moment equation as equation number 9. Now we will plot this equation in order to find the shear force and bending moment diagram. So first, if you take this equation, so if X is equal to 0, we will have B is equal to W into A. Let this point is, if you have proper value, you can plot it correctly. Let this point is WA. So for X is equal to 0, V is equal to WA, which is plotted over here. Now at X is equal to L, at X is equal to A, because X is equal to A, V will become 0. So at this point, this shear force will become 0, because at this point shear force is 0. So what we will do, we will have to join them, these 2 points. So this is the for region from A to B. Now we will move toward B to C. So for B to C shear force equation is 0. So it means from B to C there will be no shear force. The shear force will be 0. Now for region C to D, so shear force equation is this one. So if X is greater than L minus A and X is equal to L. So if you put X is equal to L, clear? So this L and this L will be cancelled and we will have V is equal to minus W into A at x is equal to L. So this will be, this is the point, so this will be minus W into A. So again you have to join these two points. So this is point A, and this is also at a distance from A, you can say. So this equation, this, if I shade it over here, so this will be your shear force diagram for the above beam. Now we will come toward bending moment diagram. So for bending moment diagram, we will move to, we will have equation from x is greater than 0 and less than A. So this was the equation. Now if you put x is equal to 0, so moment will be 0. So at this point the moment will be 0. Clear? Now at x is equal to A, if you put A, so if you put x is equal to A, so moment will be equal to W into A square minus A square over 2, which means WA square over 2, a positive value, which means if you take this point is WA square over 2. So at this point, the point will be like this. Now the shear force is a linear equation, and you can see that bending moment equation is second order degree equation. So it will be not straight. Instead, it will be a like curve. This will be a like curve, and it can be easily or accurately found if you have the proper x and different values available. Now from point B to C, we will move to from point B to C, and the equation, bending moment equation, is 1 over 2 A W into A square. It means from B to C, this point, from this point to this point, it will be the same. There will be no change in the bending moment diagram. Now from point C to D, so this is the equation. This is the equation. You can see if you put x is equal to L, so this will be equal to 0, and this will be, let me solve, at x is equal to L, W into this term will become 0 plus 1 over 2, and this term will become L minus L whole square. So this will be also 0. So this will become equal to 0. So it means that at this end this will be 0. Again you can see that the shear force equation is the first degree equation. So it will be again a curve type, not a straight line. So it will be a curve equation. So you can see that shear force is 0 or minimum at this point. So at this point the maximum bending moment, which is omega or WA square over 2. So this is your, this shaded portion is your bending moment diagram for the above beam. Let this is point B, this is point C, and this is point D, and this is point A. So that was all about this problem 5.6. I hope you have enjoyed the video. If you have any question, you can ask me in comment section. Thank you.